Tina here, and today I'd like to talk about differentiating sine and cos from first principles. You'll usually come across this topic during year 2 of your A-level course. I have made other videos on differentiation, so I'd recommend you watch those ones as well. In particular, I'd recommend you watch my year 1 video on differentiation from first principles if you haven't already. I'll show you how to differentiate both sine and cos from first principles. And you can learn these proofs to have up your sleeve for when you go into your final exams. Let's start with differentiating sine from first principles. So example 1, given that x is measured in radians, prove from first principles that the derivative of sine x is cos x. You may assume the formula for sine a plus or minus b, and that as h tends towards 0, sine h over h tends towards 1, and cos h minus 1 over h tends towards 0. Those results here may seem a little bit random at first, but they're essential to the proof later on, as you'll see. As with any first principles, you always want to start by looking at the formula for first principles given in your formula booklet. I then like to write down what is f of x that I'm interested in. So in this case, the function we're trying to differentiate is sine x. I also like to write f of x plus h. So in this case, sine of x plus h. Then it's just about subbing into the formula. So underneath the first principles formula here, we can write f dash of x, or the derivative, is going to be equal to the limit as h tends towards 0 of f of x plus h, which is sine of x plus h in this case, minus sine x all over h. At this point, we can see we've got sine of x plus h, and this is where the sine addition formula is going to come in handy. So if you look in your formula book for the sine a plus or minus b formula, it will look like that. And you can then apply that to sine of x plus h. If we sub that into the formula, we'll get sine x cos h plus cos x sine h. We can then take this entire expression and substitute it into our first principles formula. So f dash x is the limit as h tends towards 0 of that entire thing there. So sine x cos h plus cos x sine h minus sine x all over h. And once again, that part just comes from the addition formula. The next step is to actually factorize, because there are two terms here that both involve sine of x. So we can say this is going to be equal to limit as h tends towards 0 of sine x, and then brackets cos h minus 1, once you factorize, plus cos x sine h all over h. And that's from factorizing the sine x outside the bracket. From here, we can now write this as limit as h tends towards 0 of sine x, big brackets, cos h minus 1 over h, plus cos x sine h over h. Now, the reason I've done that is to split up the terms so we can use the facts from the question. So remember, we were told that as h tends towards 0, sine h over h tends towards 1, and cos h minus 1 over h tends towards 0. We're now going to use these facts in our proof, because we can actually say then that this is going to be equal to sine x 0 plus cos x 1. And that comes from this part here. If you look at this, anything times 0 is 0, so that will disappear, and you're just going to be left with cos x as required. And that's it. Example 2, very similar, but this time it says, given that x is measured in radians, prove from first principles that the derivative of cos x is minus sine x. Again, you may assume the formula for cos a plus or minus b, and that as h tends towards 0, those facts are true. So we'll start again by looking at the formula for first principles. And then I like to write f of x equals cos x this time, and f of x plus h, therefore, would be cos of x plus h. Following the formula, f dash of x equals the limit as h tends towards 0 of, this time, cos x plus h minus cos x all over h. We can take this and replace it with what will come out of the addition formula for cos, which is here in your formula book. So cos x plus h is cos x cos h minus sine x sine h. I'm going to take this whole thing and sub it in. So the next line will be limit as h tends towards 0 of that whole thing up there minus cos x all over h. Next step is very similar to the other proof. You just need to factor out the cos x this time. If we factor out cos x here, we're going to get cos h minus 1 minus sin x sin h all over h. And then we're going to split this up into two separate terms again. So this is the limit as h tends towards 0 of cos x and then big brackets cos h minus 1 over h minus sin x sin h over h. This will allow us to use these facts here, because we're now considering what happens as h tends towards 0, and these things will be 0 or 1 depending. So in this case, we're going to have cos x and then 0 minus sin x 1. Anything times by 0 is 0, so we're just going to be left with minus sin x as required. That's it for now. If you found this video useful, please do remember to like, comment and subscribe to my channel if you haven't already. And do share this with anyone else you think might find it helpful. Thanks and see you next time.